Hi all, we're going through chapter 8 now, so periodic relationships among the elements. So in this first topic in chapter 8, identifying the electron added or removed to form an ion from an s or p block atom. We know anions will gain one or more electrons to become negatively charged, and we know cations will lose one or more electrons to become positively charged. So some classifications of elements we've seen before mostly. So noble gases are here. The lanthanides and actinides are here. We haven't really looked at those too much other than knowing they are in the F block. So these elements will have electrons that go into the F orbitals. Then in the middle here, these are our transition metals. We know they can form, some of them can form more than one kind of cation. So they're sort of less predictable here as transition metals. Then this new piece of terminology, these representative elements, these are our group 1 and group 2, along with all of these elements, so the S and P block elements. Other than helium, because helium is still considered a noble gas. So representative elements, group 1A, 2A, 3A, 4A, 5A, 6A, and 7A. From what we studied in chapter 7, we're starting to recognize that we can look at the periodic table and say n equals 1, 2, 3, 4, etc. And then an element here, for example, lithium, that will have one electron in its s orbital. Then something like beryllium or magnesium here, they will have two electrons in their s orbitals. So NS1 is the general format for the electron configuration, NS2 for here. So for group 2A, where N can be 1, 2, 3, 4, etc. Once we go over into the P blocks, that's also where we focused on, so mostly the S and P block. These will all have filled s orbitals, so NS2, that is filled. Then we'll start to fill the p orbitals, so NP1, 2, 3, 4, 5. When we fill the p orbital with NP6 and still NS2, that's when we get into our noble gases. These noble gases are all happy because they have a complete octet. What does that mean exactly for them to have a complete octet? Well, they have 8 electrons in their outermost shell. We define shell as the value for N. So if we take a look at neon, for example, neon has 10 electrons to put into orbitals. So we'll start with NS2, 2S2, that's 4 electrons already. Then 2P6. So we're thinking that noble gases have a complete octet. That means 8 electrons in their outermost shell. Here I'm seeing 10 electrons. So what does this mean for them to have 8 electrons in their outermost shell? So the outermost shell here is the higher value for N. So we no longer look at the 1N, the 1N energy level. We're looking at 2S2 and 2P6. So in the outermost N, the highest value for N that those electrons fill for a given element, there's 2 electrons for N equal 2. And for the s orbital, then there's 6 more electrons still for N equal 2, but for the p orbitals. This totals up to 8 electrons. This is why neon has a happy complete octet. Exceptions to the octet rule, we're going to have hydrogen and helium. So hydrogen only has 1 electron, so that's a 1s1 configuration. Helium only has 2 electrons, so that's 1s2. Both hydrogen and helium are happy with a duet, is what we call it, with 2 electrons here in their outermost shell. So helium already has 2 electrons in its outermost shell. It is happy, it has a complete duet. Hydrogen will look to either gain an electron or lose an electron. So it also has a either filled duet or it has no electrons at all. So that's another stable form of hydrogen, to have no electrons or to have 2 electrons. When hydrogen has no electrons, that's H+. If hydrogen gains an electron, it already had one, it becomes H-. So this form has 0 electrons, this form has 2 electrons. We will talk more about octets and duets, especially as we get into bonding and drawing Lewis dot structures. Then for the F block elements, those are here. For the D block elements, we're going to fill D1, so 1 electron here, 2 in the D orbitals, 3, 4, 5, then 6 electrons in the D orbitals, 7, 8, 9. And here we would fill all of the d orbitals, and that can hold 10 electrons because there's 5 d orbitals, and each orbital can hold 2 electrons. So as mentioned here, these alkali metals all have one s electron. All the alkaline earth metals in group 2A, these all have 2 s electrons. Then in group 3A, these elements all have 2 s electrons and then 1 p electron. Group 4A, still 2 s electrons because those are filled, then 2 p electrons. We have to fill the s orbital first before we go on to fill the p orbital, so these all have a complete filled s orbital. Then 1 p electron, 2, 3, 4, 5, etc. Where the noble gases, aside from helium, all have a complete s orbital and a complete p orbital. Helium only has 2 electrons to work with, so it is happy and complete with this duet of 1s2, so 2 electrons here. And then those other noble gases, aside from helium, they all have 2 s electrons and then 6 p electrons. That is why we consider them to have a happy, complete octet. We're not concerned with the electrons in the lower n levels, so like 1s2, 2s2, 2p6. To be a happy complete octet, we're looking for 8 electrons in the higher n value. So we're n equals 2, 2 electrons, n equals 2, 6 electrons. That totals up to 8 electrons in the outermost shell, or the higher value for n, the outermost shell. So that was group 1A, 2A, 3A. Then in the middle here for the transition metals, these are 3B, 4B, 5B, 6B, etc. groups. Group 7B will have 5 d electrons. Group 12B over here will have 10 d electrons. Remember, D can hold 10 electrons in total because it has 5 orbitals for D-shaped orbitals or D orientation. So there's 5 of them. They can each hold 2 electrons. If we completely fill the D orbitals, that's 10 electrons in total. So pretty early on, we connected that these all form +1 ions, these all form +2 ions. Then we focused on the halogens as well, as always forming -1 ions. It turns out now with our knowledge of electron configurations, we can see why these prefer to form +1 ions and these prefer to form +2 ions and -1 ions here for the halogens. To become +1, it means they are losing 1 electron. To become +2, they are losing 2 electrons. To become -1, they are gaining 1 electron. The goal for all of these is to have a happy complete octet with 8 electrons in their outermost shell. So we will see then why these prefer to lose 1 electron to be +1. These will lose 2 electrons to become +2 for our alkaline earth metals. So as mentioned, based on their location in the periodic table, losing 1 electron for those alkali metals, group 1A, they will form a +1 charge in order to give them noble gas electron configuration, which translates to a filled happy octet. So noble gas electron configuration, a happy complete octet. Then the alkaline earth metals in group 2A, these will form +2 ions, meaning they are losing 2 electrons, still for the same goal to reach a happy complete octet, or in other words, noble gas electron configuration. Noble gases have that happy complete octet, or if it's helium, have a happy complete duet. Noble gases are really stable, they're really unreactive because they have a filled outer shell. Other elements will attempt to have a filled outer shell to resemble the electron configuration of noble gases, because a happy complete octet means more stable ultimately. So that was group 1A and group 2A. Group 3A, we also saw those will mostly form +3 ions. Group 4A is harder to predict because they will either need to gain 4 electrons or lose 4 electrons to have a happy complete octet. So group 4A, a little bit less predictable. Group 5A, however, will form -3 ions. That means they are gaining 3 electrons to fill their octet. Group 6A elements, these all have 6 valence electrons. So we saw that towards the end of chapter 7. If these all have 6 valence electrons, they need 2 more electrons to have a happy complete octet. That is why group 6A elements will form -2 ions, because they're taking their 6 valence electrons, adding 2 more to become -2. As they're adding on 2 more electrons, they are reaching that happy complete octet. So 6 valence electrons originally, plus 2 more, that leads to 8 valence electrons, a happy complete octet. Our halogens already have 7 valence electrons. They gain 1 more to have them be 8 valence electrons for a happy complete octet. So group 7A, these will form -1 ions. We know the noble gases won't really form ions because they're already stable with their happy complete octet or happy complete duet. Let's look at an example of how these ions do form and why they're stable as ions. Let's take sodium for instance. We know sodium is an alkali metal. It likes to form +1 ions, but why is that? So we locate sodium here, and using the noble gas electron configuration, we can see that neon has 10 electrons. So to write out the electron configuration for sodium and using the noble gas, we can say neon to represent those 10 electrons. Now we have 1 more electron to account for. This is n = 1, n = 2, n = 3. These are S block elements, so we're going to form 3s. There will be 1 electron left in 3s. This is neutral sodium. Sodium likes to form +1 ions. When it forms a +1 ion, that means it lost 1 electron. Why does it want to lose 1 electron to form a stable +1 cation? Well, when it does that, it loses this electron in the 3s subshell, just leaving a noble gas configuration or a happy complete octet. Let's remind ourselves what neon is again. So that is 10 electrons, 1s2, 2s2, 2p6. When sodium loses this electron in the 3s subshell, it has the same electron configuration as neon. Neon has a happy complete octet. For n = 2 here, 2 electrons plus 6 electrons, that's a happy complete octet. So 8 electrons here in the outermost shell, and that outermost shell is where n = 2. So in looking at them filling their octet, we're not concerned with the lower value for n or the lower shell. We're just looking at the higher values for n, so n = 2 and n = 2. So when sodium loses that electron, it loses it from 3s, so it can be a happy complete octet element with noble gas electron configuration. Then, for instance, calcium, an alkaline earth metal, it will lose 2 electrons to reach a happy complete octet and to form those +2 cations. So Ca2+ has a happy complete octet. It pretty readily loses those 2 electrons to have a happy complete octet to reach noble gas configuration. Aluminum tends to form +3 ions, so it will lose these 2 electrons here and 1 here to also have noble gas electron configuration. Hydrogen, we know, is one of our exceptions. It just wants a complete duet. So when it gains an electron, it'll have 1s2 electron configuration, which is that of helium. Hydrogen doesn't want a happy octet. We're not going to force 6 more electrons into its atom. So hydrogen is good with a duet rather than an octet. And helium as well just wants a duet. Then fluorine is one of our halogens. It wants to gain an electron to become F-. Why would it want to gain an electron? Well, originally, neutral fluorine is 1s2, 2s2, 2p5. When it gains an electron, it becomes more stable because now it has a happy complete octet with those 8 electrons in the outermost shell. We can look at the same thing for oxygen. It's going to gain 2 electrons to become 2-. It'll gain those 2 electrons in the 2p subshell to reach a happy complete octet. So there's a term for this when elements all have the same number of electrons. We call this isoelectronic. For elements to have the same number of electrons, one of them has to either gain or lose, because just the neutral forms of the elements will all have different numbers of protons and electrons. So how's this going to work? Well, neon, we know, has 10 electrons. When sodium is neutral, it has 11 electrons. The cation of sodium, though, lost 1 electron, then it ends up with just 10 electrons. So Na plus has 10 electrons. Neon itself already has 10 electrons, the neutral form of neon. Aluminum 3 plus, well, originally aluminum would have 13 electrons. When it becomes a +3 cation, it lost 3 electrons. So aluminum neutral, 13 electrons, but aluminum 3 plus, only 10 electrons, so it is also isoelectronic, along with neon and sodium plus. F-, well, fluorine has 9 electrons, but when it's in its F- form, its anion form, it's gained an additional electron to become 10 electrons total, or the same as neutral neon. So these are all isoelectronic with one another. So F- is isoelectronic with Al3+, is all isoelectronic with sodium plus. So isoelectronic atoms, they all have the exact same number of electrons. For this to happen, we're going to have some cations and some anions. Because the neutral form of every element, they'll all have different numbers of electrons. How does that work? Well, if this atomic number is 8, neutral oxygen then also has 8 electrons. Nitrogen's atomic number is 7, so it has 7 protons and 7 electrons when it's neutral. So for all of our neutral elements, they won't ever have the same number of electrons. We have to introduce cations and anions for those isoelectronic species to work. So isoelectronic, they all have the exact same number of electrons. With that, that leads to them all having the same ground state electron configuration as well. Then our transition metals get a little bit more unique, but let's talk about those forming cations. For example, neutral iron, 4s2, 3d6, with argon here as its base. So here's iron here, argon first, then it fills this s orbital with 2 electrons here, then we're into the d orbitals, so it'll fill 1, 2, 3, 4, 5, 6 electrons in that d orbital for neutral iron. So for iron's electron configuration, it's argon, then 4s2, then remember we go down in n value, so that's 3d6. So for iron, that's 4s2, but then remember for the D block, we start with 3. So this is our 3D block, 4D, etc. So 4s2, then we go back down to 3D. In order of increasing energy though, it's 4s and then 3D, and that's back from chapter 7. So for neutral iron, 4s2, 3d1, 2, 3, 4, 5, 6. Going back to naming, we know we can either have iron 2 or iron 3. Iron 2 means it's Fe2+ form. It lost 2 electrons. Iron 3 is Fe3+. That lost 3 electrons. An important consideration here is that the electrons, when they're removed from the higher value for N. We're not removing electrons from the d orbitals. We are removing electrons from the higher value for N. So that's actually from the s orbital first. So we remove electrons from the higher value of N first. So 4s2, 3d6, Fe2+ means we're losing 2 electrons. Those 2 electrons need to be removed from the higher value for N. So N equal 4, N equal 3. We need to remove those 2 electrons from 4s first. So Fe2+ no longer has any electrons in the 4s subshell. It's just argon and 3d6. Fe3+ now, we've already removed those electrons from the 4s subshell. Now we take away an electron from 3d. So this is argon 3d5. Again, no electrons remaining in the 4s subshell because we remove electrons from the subshell with a higher value for N. So N equal 4 electrons get removed first over the 3d electrons. We can see this for manganese as well. So here's 4s2, 3d5. When that 2+ cation forms, we again take it away from the N equal 4 before we take electrons away from the 3d. N equal 4 is higher than N equal 3. So again, those 2 electrons are removed here from the 4s subshell first. So removing electrons from the higher value for N, the subshell with the higher value for N first. Let's try this practice problem. So for each atom in the table below, write down the subshell from which an electron would have to be removed to make a +1 cation, and the subshell to which an electron would have to be added to make a -1 anion. This row has been completed for us. Because hydrogen only has 1 electron, it's 1s1 electron configuration. To either add or remove an electron from here, it's going to add an electron to 1s1 because this isn't filled yet. And then to remove an electron, it would have to be from 1s as well because that's where the electron is. We only have 1 electron present for hydrogen. So let's figure this out for calcium, sodium, and boron as well. To do this practice problem, we are going to need to practice writing out their electron configurations like we did in chapter 7. Then, if an electron is added to the atom, the Pauli exclusion principle will tell us that it must go into the unfilled orbital with the lowest energy first. We can abbreviate this as LUAO, or lowest unoccupied atomic orbital. That's where we would add an electron to the atom. If we are removing an electron from the atom, however, it has to come from the highest energy occupied orbital. We have to have an electron there that's occupied, or that's occupying the orbital, to remove it. Just using an example with N equal 1 and N equal 2 for the S-shape orbitals, we would not want to remove an electron from the N equal 1 sphere because that's closer to the nucleus, it's at a lower energy. We would want to remove an electron from N equal 2, it's further away from the nucleus, it's easier to remove. Less energy is required to pluck away an electron that is further from the nucleus because the positive charge of the nucleus will pull these electrons in more strongly. So when removing an electron, it needs to be from the highest energy occupied orbital. We can abbreviate this as HOAO, or highest occupied atomic orbital. We'll practice with both of these and we'll see what we mean by LUAO and HOAO. The D block elements and the F block elements get a little trickier. Here we're only looking at S and P block elements. So for all of the S and P block elements, not just the ones in our practice problem, we can follow these guidelines. For S and P block elements with unfilled valence subshells, i.e. not at the end of a block, what does that mean if they're not at the end of the block? Well, these are not at the end of the S block. So for lithium, for example, its outer filled orbital is 2s1. That's not completely filled, so we could technically add on another electron to the 2s subshell. However, if we were looking at beryllium, that is already 2s2. We can't add an electron to the 2s subshell because it's already filled. Similarly, for the P block, these ns2 and p6 noble gases, we can't add any more electrons to this P subshell because it's already filled. So for elements that are not at the end of the block, the highest occupied atomic orbital will be in the same subshell as the lowest unoccupied atomic orbital. For example, for oxygen is here. So oxygen's electron configuration, that's going to be 1s2. Now we're in the n equal 2, and we fill this one as well. So we fill the 2s2. Then we're going on into the P block. We're going to have 1, 2, 3, 4 electrons to fill in the P block. For the 2p subshell, that can hold 6 electrons in total for the 3 different p orbitals, px, py, pz. Those 4 electrons then will be placed in as 1, 2, 3, 4. This 2p subshell is occupied with electrons, certainly. It's also not fully occupied, so it's also unoccupied. If it's partially unoccupied, we could, in theory, add in an electron here and here. That means the highest occupied atomic orbital is 2p. It's also the lowest unoccupied atomic orbital. 2p is what we call our subshell, right? So this is one orbital, a second, and a third. So within the 2p subshell, we do have these that are partially occupied. This one is fully occupied. Again, in the 2p subshell as well, this is unoccupied and this is unoccupied because we only have 4 electrons for neutral oxygen. So both the highest occupied orbital and the lowest unoccupied orbital both fall in the 2p subshell. Next, for elements at the end of the S or P block, the highest occupied atomic orbital will be in the subshell corresponding to that subblock. But then the lowest unoccupied, we need to go up an energy level because we've already filled that subshell. For instance, for argon, it's at the end of the P block. The ground state electron configuration for argon is neon, then 3s2, 3p6. So for argon, we can't add any more electrons in the 3p subshell because it's already filled. That means the lowest unoccupied atomic orbital needs to go up an energy level. After 3p comes 4s, so if we're adding on an electron, it has to be in the 4s subshell, again, because the 3p is already filled with those 6 electrons. So with these guidelines, let's go through each one by one. Let's start with calcium. To assign the electron configuration for calcium, let's use the noble gas configuration to simplify how much we need to write out. So argon is the first one that comes before calcium. Then we're in n equal 1, n equal 2, 3, and 4. So we're going to fill 4s because we're in the S block, 4s1 for potassium, 4s2 for calcium. So we could remove an electron from 4s2, but if we need to add on another electron, this S subshell is already filled. What's the energy level that comes after 4s, going back to chapter 7? Well, this is n equal 4, but we know for the D block, this is now n equal 3. So after 4s2, the next one up is going to be 3d. If we needed to add on electrons to calcium, again, it can't go into 4s because that's already filled. We would have to go into the next energy level, which is 3d. Let's check out sodium now. Sodium is here. Let's also use the noble gas configuration to shorthand how much we need to write. So that's neon. Sodium is going to be 3s. Is it 3s1 or 3s2? There's only one more electron for it to fill, so that's 3s1. We can add on another electron to 3s because this isn't filled. We could also take an electron away because we have one electron present in the 3s subshell. Now let's look at boron. So boron is here, and we're in n equal 1, n equal 2 still for the p block. We follow that same numbering system. But when we get to D, that's when we start over with n equal 3. For a p block element, this is still n equal 2. So for boron and using the noble gas configuration of helium, we're going to fill 2s2. Then we're in the p block over here, so that's 2p. How many more electrons then? Just one more. Helium accounts for 2 electrons, 2 more, so 5 total. That matches up with neutral boron. We could remove this electron from 2p. We could also add on an electron here because 2p subshell is not filled for boron. So for the highest occupied atomic orbital, this is where we would remove an electron. For the lowest unoccupied atomic orbital, that's where we'd have to add on an electron. So adding on, we're looking at the lowest unoccupied atomic orbital. To remove an electron, we need that to be occupied with some electrons so we can take it away. So we're looking for the highest occupied atomic orbital. These were given to us in the problem. For calcium, the highest occupied atomic orbital is the 4s subshell. Then the lowest unoccupied atomic orbital is 3d. So 4s and 3d. Then for sodium, this 3s subshell is both the highest occupied and lowest unoccupied because we haven't completely filled it, so we could add an electron here to then have this be 3s2. So 3s and 3s, we could either add one electron, so either add one electron or take one away, both from the 3s subshell. Then for boron, 2p, that does contain an electron we could take away. We can also add on more electrons to the 2p subshell because this is not yet filled. Where filled would mean it has 6 electrons here in the 2p subshell. So boron here is 2p and 2p as well. There is example 8.1 in the main slide deck. There's also a good reminder there on para versus diamagnetic. As a reminder here, paramagnetic, these are orbitals with unpaired electrons or parallel spins, whereas diamagnetic means that all electrons are paired. For example, for diamagnetic, this means that all electrons are paired. For paramagnetic, we'd see just one unpaired or a parallel spin on its own, not yet paired with a second electron. For another example, if we're looking at the 2p subshell, for instance, if there are only 3 electrons present, these are all unpaired. That would mean it's paramagnetic. If we add on an electron, these are still unpaired. That's still paramagnetic. We consider it diamagnetic when there are all 6 electrons and all electrons are paired. So again, example 8.1 for a good refresher on para versus diamagnetic. Then in this next topic is understanding periodic trends in atomic size. To get to this trend, we need to talk about the effective nuclear charge, or represented by ZEFF. This effective nuclear charge is the positive charge felt by an electron. What sort of positive charge do electrons feel? Well, here's a hint: nuclear. The nucleus has positively charged protons and neutral neutrons that the electrons will feel, and depending on what shell the electron is in, they'll either feel that pull more from the nucleus or less from the nucleus. If there are electrons in this lower shell, they will also sort of prevent these electrons in higher up shells from feeling that pull as much as they would if they were closer to the nucleus. So further away from the nucleus, more electrons in these lower shells lead to these electrons feeling less of a pull towards the positively charged nucleus. What connection can you make between the effective nuclear charge and the radius of an atom? The smaller the effective nuclear charge, the larger the atom. The smaller the pull these electrons feel towards the nucleus, the larger and more spread out that electron cloud density will be. So less pull towards the nucleus leads to a larger atom. Those electrons are not held in as tightly when there's a smaller effective nuclear charge. For a larger effective nuclear charge, we have a smaller radius because those electrons are pulled in more tightly towards the positively charged nucleus, leading to a smaller atomic radius. There is a predictable trend with effective nuclear charge. The effective nuclear charge for elements increases as we go from left to right, and it increases as we go from top to bottom. Why do we see this trend generally? Well, it's because the number of protons in an atom increases as we go from left to right. The atomic number increases. As we're adding on more and more protons to the nucleus, those protons can pull in the electrons more tightly. So the increasing effective nuclear charge, more protons, we see this increase from left to right. We also see this increase as we go down a group or down a column. These elements here all have higher atomic numbers, meaning they also have more protons as we go this direction on the periodic table. So if effective nuclear charge increases from left to right, it's going to be a high effective nuclear charge here, but it also increases down a column. So something like this here will have a really high effective nuclear charge, or a really large effective nuclear charge down in this direction on the periodic table. More protons, they will pull in those electrons more tightly towards the nucleus. That's what we call a higher effective nuclear charge, or how much positive charge is felt by an electron. And so the way we measure atomic radii, you would probably think it's something like this. It's actually a distance from the center point to the center point. So for elements that exist as diatomics, what is that family again? The family of Brinkelhoffs. So like Br2, for instance, bonds like this. And again, we'll get into Lewis dot structures and bonding very soon in the semester. So the radius of the atom is defined as 1/2 the distance between the centers of the atoms in the molecule. Remember, this is considered a molecule and not a compound because these are not each unique elements. For something to be a compound, it would have to have 2 unique elements. So like H2O, for example, has both hydrogen and oxygen. So that's actually how we measure atomic radii. So this distance to this distance. And just a good refresher on our Brinkelhoffs and a molecule versus a compound. Where water is definitely a compound, but something like Br2, that is a molecule. we don't have two unique elements, so we describe those as molecules versus a compound that does have two or more unique elements. So now connecting effective nuclear charge to the trends of atomic radii. As effective nuclear charge increases across a row, so increases this direction, those electrons are held more tightly to the nucleus, leading to smaller atoms as we go across a row. So this arrow here shows increasing atomic radius. That complements increasing effective nuclear charge from left to right, then increasing atomic radius from right to left. Again, the smaller the effective nuclear charge, the larger the atom. The greater the effective nuclear charge, the smaller the atom. So that's the trend we see here. And so effective nuclear charge helps us look at the left to right and right to left trends. But now going down a group. Atomic radius increases down a column as the outermost electron is in a higher shell or higher value for n. As we add on more and more electrons, more and more shells, we're definitely going to end up increasing the size of the radius. More electrons that are further from the nucleus will see an increase in size of atomic radius. So increasing atomic radius from right to left, increasing atomic radius going down a column or down a group. And so as mentioned, some additional context here, as the effective nuclear charge increases across a row, so this direction, the electrons are held more tightly to the nucleus, leading to smaller atoms as we go across a row from left to right. So smaller size atoms as we go from left to right. Then atomic radius generally increases down a column as the outermost electron is in a higher shell or higher n level. As the n level increases, the distance of the electron from the nucleus also increases. We're going to see a larger atomic radius with more electrons added to higher energy shells or higher n levels. Somewhat expectedly, the transition metals, there are some exceptions. We're mostly going to focus on the main predictable trends for atomic radii. Now, an important connection to think about here is the neutral atom versus the ionic form of certain atoms. If we have cations, that means we removed one or more electrons. As we remove electrons, but we're keeping the protons the same, and just as a reminder here, the protons dictate the identity of the element. If you change the number of protons, we completely change the element. So we're keeping the protons the same, but for cations, we're removing one or more electrons. So neutral lithium is a certain size. When we remove one electron, the protons that are there can pull in those electrons more tightly. So the radius here, about 160, then it goes down to only about 55 when it's lithium plus. So the cation form is much smaller than the neutral form because there's less electrons for those protons to pull in towards the nucleus. Conversely, though, for anions that have gained one or more electrons, those are going to increase in size. Neutral fluorine compared to F-, we've added on a whole additional electron that increases the size of the radius. Those additional electrons, either one or more additional electrons for an anion, that causes sort of crowding around the nucleus, leading to those electrons not being held as tightly and strongly towards the nucleus. So anions are larger than their parent atoms, whereas cations are smaller than their parent atoms. Electrons taken away, it gets smaller. Electrons added, we increase the size of the radius. And so here's another visual where cations are always smaller than the atom from which it is formed. Lithium neutral, we form lithium plus, it lost one electron, it can get smaller because those protons can pull in the remaining electrons more easily. Then fluorine neutral is a certain size. When it becomes F minus as an anion, it's going to increase in size. So the anion is always larger than the atom from which it is formed. Then here's a nice visual as well, just to look at some common ions like lithium plus, sodium plus, our halogens, F minus, so fluoride, chloride, bromide. And just to point out here the scale, these are all in units of picometers, so really, really small. So within this visual, we can see that metals will lose electrons. We know that. Our alkali metals will lose 1 electron, alkaline earth metals, 2 electrons. Our transition metals vary. Sometimes they lose 3 electrons, 2 electrons, etc. Because metals lose electrons predictably to become cations, we remember that the cations formed are smaller than the parent atoms. Then another detail here is that as the ion charge increases, the size of the cation decreases for a given atom. For example, iron 3 versus iron 2. We can't change the number of protons because that's the identifying factor of an element. So Fe3 plus has lost 3 electrons, Fe2 plus just 2 electrons. When we lose 2 electrons, it's going to be a smaller atom. But when it loses an additional electron, so 3 electrons in total, those remaining electrons can be pulled in even tighter. So neutral iron is larger than iron 2 plus, but that's a little bit larger than iron 3 plus that has 3 less electrons versus 2 less electrons. Then additionally, the size of the cation generally decreases across a row. For example, the cesium ion with a charge of +1 is larger than barium with a charge of 2 plus. So 1 electron is lost here, but 2 electrons are lost here from their neutral forms. When cesium loses 1 electron, it gets smaller, but when barium has lost 2 electrons compared to its parent atom, it's even smaller. So the size of the cation generally decreases across a row. So smaller, larger. Decreases across a row, so technically larger here and smaller here. Then the nonmetals typically form anions. When they gain electrons, the anions formed are larger than their parent atoms. As the ion charge increases, the size of the anion will also increase within a row. So nitride, 171 picometers, oxide, even smaller, so 140. That's because this has to gain 3 electrons, but this one only 2. So this will be a little bit smaller than this. Then fluoride has just gained 1 electron, so even a little bit smaller than these two. The more electrons that are gained, the larger that radius will be. So that's this example here that the nitride ion has a 3- charge and it's larger than the oxide ion with a 2- charge. Let's try this practice problem and reorder each list in the table if necessary so that the atoms or ions in it are listed in order of decreasing size. So we'll do the largest, then decreasing size to the smaller. Before getting into that, let's go over these facts about atomic radii. We've gone through most of this, but I want to talk through these 4 important facts. Number 1 is that the atoms or ions get smaller as we go from left to right along a period of the periodic table. So within one period or one row, we get larger on the left-hand side and it decreases in size as we go from left to right. Lithium, for example, then, within the same period as carbon, lithium is further left, it's going to be larger than carbon that is further towards the right. So atoms will shrink as we go across a period because, as we know, the effective nuclear charge increases from left to right. As effective nuclear charge increases left to right, that means the atomic radii will increase in the opposite direction. Higher effective nuclear charge leads to a smaller atomic radius, because that larger effective nuclear charge means that the electrons are pulled in more tightly towards the nucleus, leading to a smaller atomic radius. So like we saw, lithium is larger than carbon, which is going to be much larger than neon. So because neon has such a large effective nuclear charge, that means the electrons in neon will orbit very close to the nucleus. They're pulled in really tightly towards the nucleus. So that leads to electrons in neon orbiting much closer towards the center, towards the nucleus. Then fact number 2, atoms or ions get bigger as we go down a group or down a column. This is less connected to the idea of the effective nuclear charge. We see this size increase instead because we're adding on more and more shells of electrons. Adding on more and more electrons to further and higher up shells leads to a larger atomic radius. More shells, more electrons, they're piled on further and further away from the nucleus. So looking at our noble gases, for example, helium is going to be much smaller than something like krypton. Then radon down here is going to be the largest within this one group or column. So to be clear, we can make these predictions more easily if we're looking at a specific row or a specific period, and if we're looking at a specific column or a specific group. It gets less clear as we're switching between groups or if we're switching between rows. And so as mentioned, atoms will grow as we go down a group because each step down a group means another shell of electrons around the atom. So n equal 1, 2, 3, 4 for the S block. Then we know we jump in here with n equal 3 for this D block. More shells, more electrons. Those electrons are further and further away from the nucleus. We're getting a larger and larger atomic radius. We can think of these shells as almost like layers of electrons. So radon has a lot of layers or a lot of shells, leading to it being a larger atomic radius than something like neon and something like helium. Then the third fact we know is that anions are larger than their neutral atom of the same element. So here's neutral. We've added on 2 electrons to oxygen for this to become oxide. You can see that this nearly doubles in atomic radius. Fluorine, 50 picometers, but then fluoride, the anion form, 117 picometers. So adding on electrons to an atom will make the anion bigger. Sometimes it's because new electrons must start a new shell. But even if we're not adding on electrons to a new shell, we're adding on electrons, we're sort of crowding in those electrons. In addition to the electrons being pulled in less towards the nucleus, when we add on more and more electrons near one another, they're negatively charged. So really those negatively charged electrons will sort of repel one another. That also leads to an increase in the atomic radius as the electrons try to get further away from one another. So they're going to take up more space. They're going to try to spread out to avoid being near a like charge. So like charges repel, whereas opposite charges attract. Then the fourth fact here, we also have seen that cations are smaller than the neutral atom, again, of the same element. It gets really difficult to compare sodium, but then the potassium cation, for example. So instead we focus on comparing sodium to the cation form of sodium. So neutral sodium, 180 picometers, then the cation form, 113 picometers. So removing electrons from an atom to make a cation makes it smaller. Sometimes that's because the lost electrons are in the last outer shell. If we remove an electron that's in the last outer shell, then we'll have a whole smaller, less layer of electrons. We'll have one less layer of electrons. But even if the removed or lost electrons aren't in that outermost shell, just fewer electrons in general reduces the general repulsion among those negatively charged electrons around the nucleus. That allows for the electrons to come closer towards the nucleus without that crowding of multiple negatively charged electrons nearby one another. Less electrons, so the cations, will be a smaller atom compared to the neutral form of the atom. So let's look at this row here. Here we're comparing argon, silicon, and sulfur. From the patterns we've seen, we know these are larger atomic radii, then go to smaller atomic radii. When thinking about the effective nuclear charge, we have a larger effective nuclear charge on the right-hand side compared to a smaller effective nuclear charge on the left-hand side. So largest to smallest, largest is silicon, then sulfur, then argon. So largest to smallest in decreasing order is silicon, then sulfur, then argon. So silicon, then sulfur, then argon. Next, let's look at Al2+, neutral aluminum, and sodium. Typically, we see that aluminum will form 3+ cations, but let's take a look at this one and see. So just looking at sodium versus neutral aluminum, we know sodium will be larger than neutral aluminum. Then comparing neutral aluminum to the cation form, this has lost 2 electrons, allowing for the nucleus to pull in those electrons more tightly. Less electrons, the smaller the atomic radius, the cation is always smaller than the parent form of the atom. So sodium will be larger than neutral aluminum, than the cation form of aluminum. So sodium, then neutral aluminum, then the cation form of aluminum. Let's try this one next. So bromide, fluoride, and chloride. So because these are all anions, we can just look at the general pattern going down a column. Going down a column, we increase in size because we're increasing the shell. So this is in the 2p subshell, this is in 3p, 4p, so we're adding on more and more electrons. That means fluoride will be smaller than chloride, which will be smaller than bromide. It didn't end up mattering here that these are anions because they're all 3 anions. If we compared F versus F minus, we know F minus will be larger than the parent atom because we've added on an electron, so F minus would be larger than F. We weren't asked about this in the problem, but just wanted to show this example as well. So bromide largest, fluoride smallest. So bromide, then chloride, then fluoride. There is also example 8.2 and 8.3 in the main slide deck for more practice on atomic radii. I hope you're all doing well, and if you have any questions about anything, always let me know. I will talk to you more next time for more on Chapter 8.